Ladies and gentlemen, hello and welcome back once again to the briefing room. My name is Eric Cavanaugh. I will be your moderator for today's event, folks, in which we're going to tackle one of the most fascinating topics, I think, in the world of information management these days. We're going to talk all about streams, doing analytics on real-time streams, on data streams. So the exact title is Continuous Intelligence, Staying Ahead with Streaming Analytics. And we're going to talk about a number of different things, including log analytics. We're hearing a lot about machine-generated data and machine-to-machine type analytics. And if you can get a handle on some of that stuff, you can make some pretty amazing things happen in your organization. So let's move through the early slides. There's yours truly. I'm on the road today, so I don't have my usual setup. It'll be hard to monitor the tweet stream, but go ahead and send your questions in using the Q&A component of your webcast console. As many of you know, the mission here at the Briefing Room is to reveal the essential characteristics of enterprise software. So we take innovative vendors and we put them into a briefing room, a live analyst briefing room with independent analysts, and we have an interesting conversation. So what we try to do is capture the kind of organic conversation that occurs when a vendor gives a briefing to an independent analyst. That's the whole idea here, and we love it. So moving right along, actually, hold on. Hold on, Mark was doodling on the screen before the show here, so he has caused me to not do a very good job. Okay, so operational real-time intelligence is what we're talking about today. Processing, monitoring, you can see alerts, triggers, actions, and so forth. And Damian, hopefully I won't steal his thunder when I mention a very interesting metaphor that he uses to describe how you can leverage these kinds of technologies to monitor streams in real time. So think about the difference between the old way of pulling data from systems, loading it into an enterprise data warehouse, building applications on top of that. Obviously, there's a latency involved. Even in so-called real-time data warehousing, still you've got some pretty significant hurdles to overcome to get the analytics in the hands of the right people at the right time. So what we're seeing now is a movement toward leveraging real-time streams. So you can think of things like the Twitter fire hose, for example. You can think about log files. You can think about any number of types of data that are fed in streams. Obviously, the stock market is a perfect example. With the stock market, you've got ticker data going all day long. There are lots of different kinds of streams that you can use, and what Damian has mentioned in the past is that with this kind of technology, it's more like looking forward through the windshield instead of looking in the rearview mirror. And if you think when you drive, obviously once in a while you look in the rearview mirror, but most of the time you're looking forward or to the side, and that's the sort of metaphorical vision that we're trying to pull off here in terms of trying to monitor and use real-time data streams. Obviously, it's relatively complex, so we'll get into that complexity and try to understand how this kind of stuff is actually done. So Mark Madsen is our analyst today, calling in from Portland, Oregon. Mark, or actually the hills of Oregon, I should say. He's the president of Third Nature. He's a regular here in the briefing room. Many of you probably know him. Happy to have him online. So SQLStream, one of the things that is worthy of note with SQLStream is that this is not a new company. So there are lots of new NoSQL databases out there these days, which are relatively new. SQLStream has been around for about a decade or so, maybe a bit longer. So they've been doing this for a while, and as you know, in the enterprise software world, when you've been around for a while, hopefully you've been able to work out some kinks, understand some customer needs, and make your technology enterprise class. So Damian Black is the founder and CEO of SQLStream. It's a pioneer in streaming big data. He's worked for almost 2 decades in Silicon Valley, as you can see, and he has a lot of experience all around the industry. So with that, I'm going to hand the keys over to Damian. And Damian, if you would just click somewhere on that slide once you get the control and use the down arrow on your keyboard to move the slide, the floor is yours.
Great. Thank you very much. Thanks, Eric. Thanks, everybody, for joining today. And I'm going to talk to you about continuous intelligence, how to stay ahead with streaming log file analytics. And our whole approach, we like to call big data on tap, so hopefully that will, a few people will relate to that. Nothing but goodness comes out of things that are available on tap. And is the slide going to advance? Let's try. The down arrow didn't work.
Just click on the slide somewhere and then use the down arrow on your keyboard. Let's see. Yeah, you got it. There you go.
I don't know. I haven't. Okay. So let's just, people don't necessarily realize quite how much information is being generated now by machines. Machines, we mean servers, computers, devices, sensors. You know, the sort of the broader terminology here. But according to IDC, we're looking at over 42% of all data. You know, within 7 years from now, actually less than that, will be machine generated, up from a much more modest 11% a couple of years ago. So it is starting to become very important, and not only that, you want to be able to leverage the data and sort of massage it into a form where you can actually start taking advantage of it, making good decisions, and being able to steer your business with increasingly real-time insights. The data arrive from many sources, location-based data from GPS sensors, smartphones, and other sort of location-aware services. Telematics from vehicles, for any kind of remote monitoring of infrastructure and services, devices, networks of various kinds, video, social media, security in the broadest sense, activity going on over anybody's service or network, applications, and so on and so forth. It's just an endless list. So if you look at actually where we are today, we have, of course, our business applications that are running, doing our day-to-day transactions, running the business, doing the things that hopefully brings in the revenue for everybody. Of course, they're operating continuously in real time in many cases. And then when we come to decision-making, we rely upon building often a data warehouse, which is historical, and the processing is performed on a periodic basis, in contrast with the real-time nature of the business that's going on, where transactions are happening as and when they happen. So what we're doing is piling up structured data, doing some kind of post hoc analysis over the information to derive some insights that will hopefully then translate into some sort of kind of strategic advantage for the company. Now, operational intelligence, what we're seeing now are sort of increasing volumes of data moving forward, because operational intelligence not only really contains all of the stuff that you want to base your business intelligence upon, but it also includes all of the information that flows in and around all of the infrastructure, all of the supporting information of your business. So, for example, in the world of e-commerce, whereas the business apps are dealing with the actual e-commerce transactions, in the operational world, you might care about all of the activity that's going on the website that's leading up to a particular purchase. So we're talking about an immense volume of data, and when you bring in not only the devices, the systems, the servers, all of the machine data, there's a lot of stuff there to process. And it's really oriented around more tactical execution. You're making decisions, you know, in sort of sub-15-minute intervals, maybe sub-second, depending on your nature of your business. And it's really covering a range of items, including optimization of your operations, ultimately trying to get to the level of automating your activities and tasks. And we like to talk about the power of V5, which is what we're focusing very heavily on within SQLStream. The volume and variety and velocity probably quite familiar to a lot of people. We are very heavily focused on the velocity end of this, trying to be able to process the data as it gushes off the various multiple fire hoses that are feeding, spraying data out from devices, systems, infrastructure, applications, operations. And we add into that visual and value. You want to be able to translate the raw information into value continuously, and you want to be able to visualize and see what's going on. And if you look at this in another way, you can look at it from the time perspective. Business applications are about what is happening right now. This is happening. This is the stuff that's generating the data, or it's what a lot of the infrastructure is there to do. The business intelligence world is all about asking what has happened and sort of drilling down into that and mining that and trying to come up with some useful insights that can change the fundamental direction of your business. Then in that case, operational intelligence is ultimately looking at what is happening and probably more importantly, what will happen. How can you really take advantage of this, try to avoid problems before they happen, and how to try and improve the business to take advantage of what you expect to happen. If you look at this from another perspective, you're going from a reactive world to a proactive world where you are, first of all, you have the first step, if you like, towards the nirvana here is to be able to collect and analyze the information in real time as the information is flowing out. And from that, try to synergize the stuff to synthesize some kind of insight that you're able to make decisions upon, the actionable insights. And then above that, what you want to do is, by looking at the synthesis of information as it's flowing, you want to be able to start making predictions about what is going to happen. Is this service about to fail? Is this customer looking like they're a good prospect? Is this someone we should give an extra discount? Any other kind of real-time decisions that actually make your business operate better than others, that's what it's all about in the world of predictive analytics. And then the final sort of the ultimate state to get to is where you can automate, close the loop now from all of the operational data that are flowing in, the machine data that are flowing in continuously, enriched and enhanced with your stored historical information to be able to automate the actions so that you will, for example, serve up the right discount to a particularly loyal customer, put in front of them the right customers and products, they take the remedial action to bring your operations or service back in line with the specification that you've promised your customers. And then if you look at the timescales again, so we're here, at the beginning it's what has just happened, the immediate collection of the event and the analysis. The actionable insights really is what is happening now. We're looking at the various stream of activity that's going on. Let's try and find out, okay, what the synthesized view is right now. And then, of course, predictive analytics is going on to what will happen in the future, or what we think might happen, and then finally actually trying to make it happen, the business decision that you want to execute. I think it's always good to start off with an example. So we want to, one of our sort of most visible deployments was with Firefox, Mozilla, monitoring all of the worldwide downloads and real-time analytics on the downloads of Firefox. So that's processing all of the log files from the various downloads servers dotted around the world, and populating Hadoop so that you actually can do, they actually then are able to provide business intelligence analytics performed after the event, but at the same time providing real-time analysis of the downloads as they happen. So how does that happen? This gives you an idea of the kind of world that we're living in. Of course, there are lots of log files that are being written to. The first thing is to turn those into streams of data that can be processed continuously in real time. And so what you're doing is parsing. SQLStream will be parses those records and generates like teasing out some of the structure from the unstructured data. And the structured tags are then added into the records so that you're actually able to understand and be able to take some reasonable decisions around what would otherwise be unstructured information. Filtering off badly formed records, anything that's happened through some kind of hiccup of the system or infrastructure, and then bringing all of the streams together so you have one large fat stream that is then processed, mapping IP address into a location, longitude, latitude around the world, looking for bots or people that are trying to game the system, where there are perhaps multiple downloads happening from a single IP address within a reasonable period of time because they want to have their little town, village, or city suddenly pop up onto Mozilla's very visible dashboard. And then once that's going through, then analyzing for any errors that might have happened during the download process, abandoned downloads and so on, then classifying the various browser types, the various locations, and any other important, interesting elements through streaming analytics that are used to populate Hadoop HBase. And then HBase can be used also then to refresh charts that are showing any kind of drill down activity you want to see at any point in time, which is the top country, the top city, the top continent, how do the various different locations compare with one another, and so on and so forth. At the same time, feeding a real-time streaming visualization. If you want to see this in action today, you have to go to Google YouTube Mozilla Glow, and you'll see any number of recordings of this this is the second generation system Mozilla Glow that was put out there. It looks a bit like a carpet bombing of the world, but that is not really what is going on. It's showing the downloads as they happen, with sort of the area around in that location lighting up, and it's quite hypnotizing as you watch it happening in real time and showing the counters going up and onward. So that's the Mozilla Glow system, and we were very pleased to actually have Mozilla put our logo up in the bottom right corner. Given that they're such a prominent closed open source technology, and SQLStream is a closed source technology, it was very heartening to see powered by SQLStream on that whole analytic execution. You can see here on the right hand, admittedly in a somewhat sort of toned down, tasteful way. So please do take a look on the internet and find that, and you get an idea of one of the first Hadoop applications that was processing real-time analytics and populating Hadoop clusters. So where is this? Where do you get this information? How do you tease out the structure? And what does it involve when you're processing the unstructured data that you're often seeing in this operational world? Well, here we see a number of different sources of information, from social to smartphones to call detail records from the telecom world, web server logs, transactions. First thing to notice is the timestamps, of course. The timestamps can be anywhere within the actual record. Of course, there are other technologies out there for processing log files, some pretty well known, such as the likes of Splunk and so on. Many of those products, including Splunk, will actually just will try to identify a timestamp, but will then promote that timestamp to be the, assuming that it becomes the representative for the entire record or row. And of course, it may be a timestamp that's embedded in the data or record, which is just there because it is an embedded time that's part of the business or operation. So in SQLStream, we try to go do a little bit better job of that to make sure that the correct fields are identified in the way that you expect and anticipate. And then we're showing some of the other information that you might want to pull together. One way of looking at this is kind of session reconstruction. Whenever somebody's using your service or transacting with you, they have a kind of they leave their fingerprints across a number of sources of machine data. It might be through the social media, it might be through telephone records, it might be transactions on your service, it might be location from their smartphone app. And the idea here is to pull together all of this information, joining all of the information to be able to reconstruct those sessions accurately and pull together the complete information about what is happening in your business, so you can then start making useful, actionable insights and going beyond into the predictive world we talked about before. So here, obviously, clearly, you're seeing the need to join information and do that on a continuous real-time basis. And that's something that SQLStream excels at, and we can talk a little bit about that during this presentation. So as we've been involved in this business, we've recently had this, I don't mean to be blasphemous now, but Aberdeen Group has just finished a survey of their customer base, and they gave us feedback that the top 3 items were exactly as we highlighted on this slide in a recent briefing. So that was interesting to get that sort of reinforcement and validation. But we see the 3 big areas as being the sort of the main pain points. It's the data explosion, the exponential growth of data that makes it just too costly to analyze data in real time. This large volume of machine data, operational data in real time with conventional approaches. It's also a problem of business agility, where it basically just takes too long for your business to be able to respond to new market opportunities or competitive threats. And finally, it's a problem of complexity. The irony is that hardware is cheaper than it ever has been. You have this multi-core, inexpensive memory, inexpensive servers, blade servers with lots of instances of servers. But and the parallel processing that you need to be able to take advantage of this inexpensive parallel hardware is more difficult than ever. It's so difficult now to write those applications, to write those sort of lock-free applications, to write systems that don't snarl up in deadlock or suffer from race conditions, multi-threading behavior. And that becomes just a problem not only of complexity, it's a problem of risk in actually ever being able to get anything working. So what we do in SQLStream is to simplify this, and we have a very simple paradigm. We take the SQL language that was originally invented for structured queries a long time ago, and we basically reinterpret it as a massively parallel data flow processing language, processing both unstructured data and as well as structured data very elegantly at very high performance. And so what we have is we have queries that are running continuously in this parallel data flow execution mode against the live streaming data without storing the data first. So we aren't storing or kind of persisting any particular structured form of the information. It's still fluid as it flows through the main memory of servers and allows you to be able to pull out whatever structure that you need, and then enhance those records with the structure as the data flow. We then look at the SQL queries. The queries just become, if you like, transformers of streams. And streams you just view as, like tables, they are sequences of records, but unlike tables, they are infinite. Records are being continually appended or added to the end with timestamps, or if there's no timestamp, we can supply one for you. And then we have queries that are processing these streams, these name streams, and performing joins, aggregations, groupings, and passing results that emit in real time from those queries, again, over the data without storing or persisting the data outside of just the sort of transitory buffers within main memory that we hold the information in, and then passes those results in a real-time basis to then feed other queries, and then maybe allow you to, in turn, feed queries, and so cascading through the network, getting you real-time insights and real-time actions, triggering real-time changes to your service, and potentially updating any number of external storage systems. So when we have those sort of basic SQL construct, then we will pull out from that the definition, the parallelism that's inherent in those very high-level queries, and we will then be able to exploit all of the hardware for you, taking away the development risk and guaranteeing that the system will run and execute correctly. So it just completely eliminates the development risk so long as you have some kind of familiarity with SQL. And then using the same kind of capabilities that have been proven over the decades, you can add new views of information to create any view of the information for any application that you want using the SQL view, and plug in new data sources without taking the system down, just like you can with databases, but now with live streaming operational data. And then finally, to provide a very scalable mechanism, because we are not transacting the data, we are transforming streams, input streams to output streams. Without transacting or side affecting the incoming streams, we are able to scale up in a way that is not possible for conventional database-type approaches where you have to synchronize state over multiple servers, and there you very quickly run into the problems of physics and speed of light and so on. So if you look at this, pictorially of what's going on, we have your machine data coming in raw, and hopefully it gets transformed through streaming technology into some beautiful, glittery information that will enhance your business. But beyond that, we actually can output any views, any derived views of the information that you care about, and store them into any of your storage systems. And we just picked a few up here in random, but we support a wide variety of these. We have very tight integration with Hadoop to be able to pull information and store information into Hadoop, to also be able, if you within HBase, to enrich streams drawn real time from information from HBase. And to be able to replay streams after the event if you want to do things like scenario analysis or testing the results of your machine learning and data mining, so that you can then determine whether your predictive analytics are working correctly by back-testing them over previous operational data before you drop them in against the live streams. And so in this process, we're doing everything from sort of cleaning and aggregating information, performing any kind of analysis that you want. We call that ETL++. Obviously, processing and analyzing unstructured data and enhancing and enriching it, so you get all of things like IP addresses changed to location in the example I said before. And then allowing you to do predictive analytics, so you can actually take action, change your service, whatever you might want to do. If you look at the existing approach in the world, what you have is a high latency mode of operation, because the classic sort of phases of data processing, of operational data, going from raw to sort of fully cooked and sharing the information, takes part in a number of steps, each of which has to stop before you go on to the next. It's true in data warehousing, where you have partitions of tables, and you want to process from one partition of the database to another. It's also true in the Hadoop world, where you'll have one iteration of over the whole HDFS space before your MapReduce jobs stop, and then the last job finishes, the next phase can start. So what we do is we flip this thing down into a low latency mode where we overlap all of these activities in continuously executing data flow operations. And instead of, if you like, having holding tanks between the various steps, we have plumbing that plumbs the stuff right the way through in real time. So you're getting continuously results flowing out as and when you need them. And if you look at what's going on in terms of the queries that you're talking about feeding other queries, and then when we compile queries down into sort of more, primitive relational operations such as aggregating records or joining two records together, what you have is a graph. So each operation, each query represents a graph of activity that you want to be performed, and then when a query feeds another query, those graphs get joined. And so what you get in this case is you get a bigger graph which specifies all of the operations that you want to perform. And this is basically a data flow graph. Data flow concepts came from decades ago, but they're just as relevant today. In fact, probably more relevant given all of the availability of inexpensive hardware, which is really perfectly designed for stream processing with its various tiers of levels of caching, high-performance interconnect networks, and multi-core processors. So we have 6 streams coming in here, 4 streams going out, and all of this stuff then specifies the computation that you want. And what SQLStream does is it just looks at this graph, it optimizes it first of all so that you don't recalculate things unnecessarily. It simplifies the queries where that makes sense, and then it maps this works, if you like, definition onto the available hardware. And then we execute the queries continuously in real time with two dimensions of parallelism. So Hadoop is great for one of those dimensions. It does the data partitioning or the SUPERSCALAR stuff where you spray data across a number of processes in parallel. SQLStream also excels at doing pipelining in addition to the data SUPERSCALAR stuff. So the left to right, if you like, along the x-axis is the pipelining, and here on the y-axis is the kind of SUPERSCALAR. And combining those, it's what hardware does today if you look inside it, and we just make sure that the computations are valid by making sure that the right timestamps line up before each, if you like, node fires and performs its task. So that's really what's going on, and that's how we achieve this sort of massive scalability on a very fine level of granular data. If you want to see what it looks like, when we want to create one of these views, well, here's a simple one. If you imagine you're just looking at your shipping operations, you could have a stream of orders that are coming in and a stream of shipments that are going out. Maybe you want to find out whether my New York orders are actually shipping on time. So what you do is you join the order stream against the shipment stream, match where the city is New York, where the order ID, match where the order IDs are the same, filter by the city of New York, and maybe do it over a 1-hour rolling window. This window construct actually is a part of the SQL standard. SQL does have support for time series analytics, and we just leverage this, though, by turning the whole thing inside out, again, running the queries continuously, rather than storing the data, then running the queries after the event. You can view this as instead of storing the data and running the queries, we kind of store the queries and run the data through the queries. A more sophisticated example was monitoring. This was done actually in conjunction with one of the third largest cloud computing company at the time we were involved in this engagement. And what we were doing was solving a problem of analyzing the operations, trying to look for problems of applications running hot. And the problem here is if you have simple thresholds in databases, that may be inappropriate. You may want to have a certain level of activity. But what you want instead is to recognize, perhaps take account for the changing workloads during the time of day or during the natural life cycle of the service during the day. And so they want to detect accelerations of error rates. And so what we do is maintain something called Bollinger Bands. It's taking a moving average and a moving standard deviation and looking for the actual metric that you're measuring. In this case, applications using CPU, the CPU usage rocketing up. And that means that not only is that customer going to get a horrible, unexpectedly large bill, but also anybody else that's sharing that physical infrastructure will have a deeply degraded service. So that's the kind of thing you want to be able to quickly identify and try and fix if indeed there is a problem. So we have a nested query to solve this. The inner query computes those analytics, the averages, moving averages, and standard deviations. And then the window construct provides this partitioning mechanism. So you can basically have a separate analytic for each, in this case, service URL, but it could be a core, it could be an application ID, it could be a subscriber number, a customer account number. And so we're maintaining millions of analytics or millions of streams, millions of these Bollinger Band calculations, all being performed with a single query. And the outer query just detects when it bounces above that threshold of 2 times. And we can process this on a 4-core commodity server around about 500,000 records per second easily. So very quickly, by adding cores or servers, you go into the area of being able to process millions of records per second. Another important element is trying to understand, you have all of the machine data coming in, you have applications wanting to take advantage of the information, increasingly now business latency being squeezed out, so they want to do this in real time continuously. So the problem is, how do you combine the records in the ways that each application requires to get the data in the format that they're able to consume and at the time that they're able to consume it? You have N sources and M consumers. You've got an M times M headache here, made worse, in fact, with siloed solutions, maybe monitoring solutions that are also you want to derive value from. Well, what we do is we look at this as a data management problem, applying the same kind of principles of managing the complexity that have proven themselves over the years now with data warehousing and databases, but do this now as a continuous real-time infrastructure. And so you just plug in new data sources, you plug in new views, and let the platform build that graph and understand how to derive and assemble for each application's view how to pull together the records, maybe combining multiple records from a single stream, combining multiple streams together, and enriching with data, historical data, to then provide a record in the time, in the format, and in the space that that application is able then to consume. Also mediating between pushing data in and pulling data in from the platform. So the push-pull both in terms of data ingestion and pulling out and pushing out results, again with the same technique, and optimizing and managing the whole process. If you want to be able to talk to various different data sources then to orchestrate any of the processing to enhance the streams and records, etc., we have a rich set of adapters covering everything from XML parsing, natural language analysis, email adapters, sockets, all of your favorite databases, obviously tightly integrated with Hadoop, and we were one of the, I think, the only streaming vendor announced at Google BigQuery launch, and one of 3 ETL vendors that were announced for that launch. So again, out of the box, where you can quickly focus on getting your applications working and not worry about the connectivity so much. Visualization, we just added visualization to the product now, so rather than just getting historical classical BI views of information of what's happened in the past, you can then pick out the various streaming definitions and then perhaps view it as a moving real-time animated graph with dancing bars. If you prefer to see a bar chart, I'll have both of those running at the same time. And then perhaps updating a map of the world showing the location of those events. And the whole thing is almost infinitely tailorable, so you could change the size of the dots on the graph based on the values of the derived values from the stream processing. So as it comes towards the end here, if you want to compare then this approach with what we call traditional operational intelligence log file processing approaches, then if you look at, for example, companies, Splunk is very much in the market leader here, so that's a good example to compare with. In contrast to that, a sort of traditional approach of where you're storing files and processing the data afterwards, what we provide is a rich time series analytics. Instead of simple pattern matching queries, we provide really complex, the full power of SQL run over time series, enhanced within time series analysis, allowing you to do full joins and correlation, to enhance the data with your databases and systems, and then to scale up to massively parallel using our DATAFLOW technology to very large volumes of information processing performed very quickly. And the idea here is to make this completely painless to be able to manage and orchestrate all of this processing of information to get your real-time insights and to be able to take advantage of predictive analytics, the data mining tools and technologies that you've got, and to be able to even automate the actions that you want to take based on those analytics. So in summary, this is how we've achieved this now. We solved the complexity problem by letting you deal with high-level SQL and letting us take the strain onto our shoulders with our sort of lock-free execution environment, allow you to be able to create new applications from the existing streams by just creating new views and adding queries without disrupting the applications, without rebuilding, without stopping anything, plug in new data sources again without stopping, insulate those applications from the changes in the data sources and any other things that you might want them not to be directly tightly bound into. And then finally, to scale up by not transacting information in databases, but basically using stream processing to allow you to scale up to the largest volumes. And then the final slide here, I just want you to sort of see is it goes well beyond IT processing. You can look at everything from the areas you can see here, smart grid, automotive, logistics, machine-to-machine, location-based services, environmental monitoring, you could add healthcare monitoring, and so on. And we are in various stages of engagement in many of these areas too. So that's the end of my presentation. Hopefully that gives you a good idea of what SQLStream is about and how we tackle the problem of machine data, processing operational data, and deriving real-time insights.
All right, good. And with that, I just gave the keys to Mark Madsen. Mark, just click on the slide and use the down arrow on your keyboard to move through.
Okay. So no animations, sorry, or the title slide would actually make sense. So just a couple of comments before I dive in with questions. Kind of going back to the architecture of a data warehouse and why some of these things are important. One being that the enterprise and enterprise data warehouse was sort of a lie perpetrated by a bunch of IT hoaxers, because in fact we aren't storing 100% of the data, and we are also doing it periodically, typically batch, typically once per day. And that creates a lot of latency problems when you're trying to do things where you need up-to-the-minute information and historical information at the same time. And we architected around some things that were perhaps a little bit different. And I think that one of the key things here is just differentiating transactions from events. Sometimes transactions are events, but most of the time when we talk event streams and event data, we're not talking just about transactions. And when we look at them, a transaction, each individual transaction has valuable data. It's got dollars and customer IDs and a bunch of other things in it, and we care if one of those transactions disappears. And there are important ordering concerns. There are not important ordering concerns. They stand alone, and you can aggregate them. You can sum up the dollars and count them and get meaningful results. But when you look at events, it's a lot different. An event stream, like clicks on a website, well, you don't want to lose them. It's pretty much the norm in the web analytics industry that you're losing up to 5% of the clicks on your website through various anomalies in the collection grids that instrument this. And the same could be said for a lot of sensor data and other event logs. And the interesting thing is most often a derivation of the set of data, not any one event, but a series. Because there's an ordering, usually a time-based ordering in this stuff. And set relational was never designed under assumptions of ordering. A set is, by definition, unordered unless it's an ordered set, which is an algebraic operation over the set. So when you think about what you're doing with SQL, you select and then you sort afterwards. That's how it's done. And so you have a bunch of things like natural ordered dependencies and noise in the system. And the other thing is that transactions are mutable. You write a transaction and then maybe you update it, you change an order status, you remove a line off of an order. When you think about events, they're usually exactly that. They're events and they get written once. They're not mutable. You don't go back and change an event, think about compliance logs and security logs. If you could go back and change them, of course, that would defeat the purpose of doing it in the first place. So, you have to start thinking about transactions and events and then about how this stuff is used in an organizational context. If you start off with collecting data, business intelligence has generally been about collecting and monitoring and running reports, looking at dashboards. And, part of that is really just hunting for exceptions. You're looking at these things in order to gauge the health of something, to see what's going on, to manage a process. And what you're really most interested in is the exceptions and then doing the analysis. And so BI and various types of analytics tools help you to analyze the causes and figure out what's gone wrong with an exception. And then, making your decision and or acting are things completely outside the bounds of the system. And that's usually a days or longer time frame, anywhere from hours to weeks, really, depending on the kind of decision you're making. Is this business program worth pursuing versus I have out of stocks in 3 stores in this district, why is that occurring? But when you start going within a single process, usually we're down in what's called programmed decisions. And programmed decisions tend to be inside of a process. You have a process defined. You're not necessarily dealing with exceptions where humans have to apply context to information to understand what's going on and maybe change a process. You're acting within a process and executing as opposed to having to make a decision. And a lot of industries have automated portions of it. This is where a lot of enterprise decision management tends to fall. It's in what's called a programmable decision, where the parameters are the same every time. The only thing that changes is the data. The question then is, why have a person do this at all? Given that the decision is bounded and you're not allowed to stray outside that boundary, you may as well let a machine do it. And if it needs moderation, you feed the decisions through a human moderator. But it's a very different path. And streaming technologies typically do this. Data warehouse, not so much, because data warehouse wasn't designed for that kind of latency, and it wasn't designed for that kind of processing. When you think about the usage model, a data warehouse is a question answering machine. You ask a question, you get an answer. When you talk about monitoring, your dashboard might refresh, your reports might refresh when data updates, but typically a person chooses the time to go and look at something. It's not the machine telling you what to do it, right? And trying to push self-service BI as an operational BI doesn't work. And given that there's lots of data and the value of events as data, other than the broad patterns, tends to decrease outside of the decision windows, you have things which don't quite match the architecture of write everything first and look at it afterwards. And you don't have the act on it as it occurs, because the best you can do is a post-insert trigger in the database or a continuous poll by a client front end. And so you have to deal with these 2 different paths. Machine managed and human mediated is really where we're going with a lot of actuation, of execution. And what we've got now is this sort of convenient transactional data which goes into the data warehouse, and it's like the old joke about the drunk who loses his keys, but he looks for them under the street light because that's where the light is. Well, that's how we've set up measurement programs. And we have all of this flowing data, much of which is not recorded because of low value of the data in and of itself compared to the cost of having to store all of that data. And yet you can operate on much of that streaming and actually only store the important bits when you need to. And so we've got this data in motion versus data at rest model, which has to be married to an environment to get a complete picture. And right now, the BI data warehouse world is firmly in the data at rest picture, but the writing's on the wall as far as what's coming towards us. And that gets us into what uses this data. When you're talking actuation or monitoring and exception triggering, you're sending out alerts based on events, or you're causing actions to occur in a system, which is a write back kind of a model. And that means you need to talk to things beyond pure SQL sometimes. Either the sources are not SQL, like message streams, or the applications that you are calling from require programmatic access. And so that's kind of where we're going with these things. So with that, I thought it would be good to sort of walk through a couple of basic questions. First off, I'm curious about one thing. You've sort of answered why SQL, but while there are temporal constructs for SQL in, things like windowing functions and such. There isn't really a stream SQL formal standard that everybody agrees on yet. So given that, why SQL, number one, in that area, and number two, how do you deal with the lack of standards given that you want to put tools on top of this?
Okay, so that's an interesting question. Surprisingly, I haven't been asked that, but I'm glad you did ask me that. Our perspective is that a lot of people that have looked at trying to provide kind of like stream processing have created their own dialects of languages because that's, number one, the SQL standard is quite large, it's quite strict, it takes quite a lot of work to be able to implement it. And particularly in the startup world, a lot of companies, have boards that are pushing and pressing on them, so they will do whatever is most expeditious. And so, and engineers, previously, once upon a time, I was an engineer. We all like to invent things as well that we want to do that are unique and different, and take their own angle on it. And so as a result, we have a whole bunch of people that have taken a completely proprietary approach to processing. I mean, whether it's Splunk or any other sort of complex event processing or any other kind of stream processing environments you might come across, they've done it their own way. However, SQL has got some pretty rich support for things like time intervals, timestamps, windows, and really they are just perfect. They were designed for doing historical queries, to do things like moving average calculations and so on after the event on stored data. But there's no reason at all why those queries should not be executed continuously in real time. The only extension that we've done is we've actually added support for joins. But all of the data types, and all of the operations, the windows, even the partitioning, that's all SQL standard. And the big advantage of that is we can test queries against DB2, against Oracle, or any of the sort of leading standards compliant, turning on the standards compliant features. We can check that they actually do work and work on those systems too. And that provides you portability of your analytics from your Oracle and DB2 type systems and any other SQL standard compliant systems to drop those then into SQLstream and vice versa. And a lot of people, there are millions of users that know SQL out there and are familiar with it. Just like English, I mean, it's not a perfect language, but it is a language that everybody speaks for data management. And if you go around the world, whether you're doing business or technology, you'll end up speaking in English. It's the common denominator, and SQL really is that for data management. And if you look through some of the examples, I presented some that were sort of, a little bit, hopefully not completely trivial examples, the Bollinger Band one, for example. But if you look onto our blog or our documentation, you'll get much more detailed examples of how we can handle most of the kinds of things you're going to expect. And we haven't had to depart at all from the SQL standard. So that's why invent a new standard if there's a perfectly good one that works that you can take advantage of.
Yep.
But don't you still have to have...
You just watch out for the background noise, guys. Go ahead.
Don't you still have some extensions that you have to make? For example, your attachment of SQL record constructs and types to a particular stream and how you map that.
We haven't had to. The only extension and the example that I showed you for it, I said we have extended now to add joins, to allow joins to happen over Windows, but aggregations and groupings are already in the standard. Those queries, I said, will run directly on databases over historical data. We have added a keyword stream, but we added that so that, if you don't have the keyword stream, it tells you you're going to return a table. So we only use that basically to protect the standard. So that it's an extension, but it's only an extension because we're running the queries continuously. But no, we haven't had to. We found that there's a SQL standard for how you extend processing beyond SQL. So you can have user-defined functions, user-defined transforms, and you have SQL Med for managing and encapsulating external data sources. You have the SQL views, and we just found that they all just work very elegantly, very efficiently, and in terms of how SQL processes other data types too, whether it's binary or other sort of representations, again, we found that works very well. In fact, the biggest irony of all is that SQL is a much, much better language for stream processing and for parallel processing than it is for database querying. And because people, when they're writing SQL queries against a large, persistent database, will tend to dumb down those queries, maybe even denormalize the data, do all kinds of things, because they are worried about the time it's going to take to retrieve information or the resources that it's going to take to execute the query. In our world, what we actually encourage people to try and take advantage of some of the more sophisticated, advanced features like various kinds of joins, these high-level declarative components, because we can then use them to tease out the parallelism and to make those things run in real time over live streaming data. And so long as we are able to keep up with the incoming stream, then we'll be able to, there is no penalty at all for being able to, for using those constructs. And it just, in fact, means that we can take advantage of more of the hardware, if that makes any sense.
Mm-hmm. So if I'm pushing into sort of analytics space, and it is something that falls outside of what I can do in a plain SQL statement, do I then use a UDF, or do you push using an application with multiple queries, using those as inputs into the functionality that I'm trying to execute?
Can you just repeat that question? I didn't quite.
Yeah. So, okay. So there's a fair amount that you can do within the confines of a single SQL statement around, analytic functions, particularly, probability and statistical functions.
Mm-hmm.
But if you get to something that requires iterative processing over that, that is not really amenable to SQL, or that is a complex calculation that's not amenable to SQL, vector or matrix calculation, or maybe trying to do a real-time Bayesian recommender or something.
Yeah.
Are there things that basically you can't do here and that you need to sort of use this as a pipe to something else? And what would the nature of those be?
So, first of all, you can do these. We have a very elegant way. If you want to do things like vector processing and so on, then, or take an even more outrageous example. Say you want to process a voicemail, and you want to do some analytics on voicemail. Now, there is a mechanism for extending beyond SQL. There's the UDX, the user-defined transforms, allows you to write. In our case, you can dynamically load Java modules that, and we'll generate the glue code for you to be able to process any number of incoming streams and generate an output stream. And so you could be processing a stream of voicemails, piping that out to, for example, a nuance server, coming back with a text string, which is the English that was from the translation of the speech fragment. Then that gets added as a field to the new record. Then you can be analyzing that natural language with GATE to try and pull out what the subcomponents are of the natural language component. You'll then pull out the keywords that you care about, maybe any numerical information, and they will get added as fields. And as the records go ahead, you then may join the records with the database and so on and so forth. So you get the idea. You can also dynamically create new schemas, new streams as you're going along, have multiple different formats of information that are, branching out from any given record stream. So that's how we handle those. The ones that cause the pain, to get to the nub of your question, it's, we are to be able to make this stuff scale out very well, we try to make things state-free, okay? So if you are relying upon a global state, you can do that through the UDX mechanism, but you're going to have problems in terms of synchronizing and getting like the deterministic behavior that we otherwise will promise. So if, for example, you join a stream against some, a random function number generator or something where the state will change for different people, you'll get different, weird results. So that's the area where you have to be aware. You want to make sure that, for the incoming streams, you're going to get the same reliable output stream. But you can do things like vector processing, and you can encapsulate stacks libraries and all of that kind of stuff, and we have done that.
Okay. Oh, it's the execution graph dynamic. If load in the stream increases, is it possible to dynamically increase the number of resources processing, or do I have to stop and restart a query to do that?
No, you can change the number of cores and some of the the metrics as the stuff is running. In terms of optimization, I mean, ultimately we want to be able to dynamically replan queries the whole time. It's somewhat limited in what we're doing in that regard. We will tend to plan the query and optimize it at the time we do that. You could pause and replan if you wanted to. But that's the goal in the end, is to have a complete, the nirvana for us. I mean, we've reached about 1.3 million lines of code, so it's been a non-trivial engineering undertaking. That's about 260,000 pages of code. Is to be able to declaratively specify, all of the information, all of the, if you like, all of the subscribers, all of the publishers, all of the people that are pushing in data and the people that want to take out data, and look at their quality of service requirements, and to be able to auto-magically optimize the whole thing and make sure that everybody gets, exactly what they want based on the what they're paying for that part of the service. I mean, that's where we ultimately believe the thing could go. Right now, obviously, we're not quite at that stage, but we are still taking this declarative model because we think it's got a lot of legs.
Well, I think that's true whether you're talking about trying to do things in MapReduce or trying to do things in a database. Declarative wins over imperative because you can't optimize otherwise.
I think particularly parallel processing is really painful. I mean, it took us years to get our system working so deterministically. You get the same results out from the same input streams. You replay stuff, you get the same results out. You don't run into race conditions. I mean, we do this in a near lock, actually pretty close to lock-free execution environment. It's very, very hard, and I think it's totally unreasonable to expect most organizations to be able to try and do that for their own data processing. So I think that's part of the beauty of this, is high-level queries, and let the system take the strain, and let it guarantee correctness for you.
Yeah, having done parallel programming, I understand where that's going. I question a lot of the sort of Java programming without dropping into parallel domain-specific languages to do it, in any kind of enterprise context. So hiding it in declarative languages works for me. I do have a question about sort of the time dynamics. If I've got multiple streams running at different rates, so like in a medical condition, you might have a blood pressure monitor going off every minute or two, but a near continuous, multiple measurements per second heart rate monitor. How do you manage the merging of these streams which are coming in at different time rates in terms of a query that's trying to somehow synchronize them and, do a join across them?
Right. Well, I mean, if you sort of think about it for a little bit, it's clear that we have to be able to process the data correctly based on the timestamps that are coming in. And so what we will do is we'll match up those timestamps and make sure the results are valid, and we'll process the records in a deterministic manner, so you will get the same outputs for the same inputs. So one of the common occurrences is that you'll get stuff that comes out in big globs. Maybe you get a device that's emitting a file every 5 minutes, right? And another one is streaming out information continuously in real time, and you want to be able to combine that information somehow. So what you do is you just define a window that's big enough to be able to process the data that are coming in. Maybe you'll create a 10-minute window, and then you know that you'll be able to do all of the joins and aggregations, and all of the records that you want to match against will be somewhere within that window. Anything that falls out of that, you'll capture as an error stream, which then has to be processed through some exception portion, and there'll be another stream processing a set of queries that are dealing with those exceptions, which may need to be fixed by humans. I mean, there's no magic here. If the data come out with crazy times, you'll have to do something weird. What we will do, though, is allow you to reorder data dynamically, so you can basically groom the data. If it's coming out of time sort, you can have, for example, a rolling, maybe it's a 5-minute window, and during that 5-minute window, what the system is, it will hold records back and ensure then that the records are emitted in time order. So we call that T-sorting. And then the combinations of those, you can, obviously each stream will have different window requirements. You can have multiple windows within a single query. You can have nested queries, queries feeding other queries. So each business rule will have its own requirements. And you'll have to understand the nature of the delays and that are involved, or the potential glitches that could come from the data sources you're processing. Did that answer the question?
So, yes, it does. And also, it sort of brings up one final question, which is the kind of interfacing with a persistent store and the replay over a longer period than, say, your minute. So I guess it's really two separate questions, but one is the insert mechanism basically SQL inserts, or can you feed into things like bulk loaders so that you're not, trashing an Oracle database or something that doesn't ingest data in real time very well? And then the second question is sort of related to the historical side. If I have an exception trigger and I see it and it's part of that, say, 1 or 5 minute window that you show in a query there, can I go back and replay what led up to that point? So maybe go back 10 minutes and watch that particular thing and see when that occurred. And how does that work?
So let's take the first one of those. For each database or data store or sink, we have adapters that can be configured. Again, declaratively configured. We use the SQL-Med interface. You specify the kind of attributes of what you want to do, and it will then just deal with that output for you. So yes, we do take advantage of bulk loading mechanisms. I mean, in some cases it's tailorable. So if you want to write it as soon as each record's available, then you can do that. So you can tune it, and of course, and you can have different instances of the adapters for different streams. We have a mechanism that we call a pump, which is a bit like a select from insert into, and it's so if you, for example, another query question you didn't ask is, but I mentioned you have streams that are going through and there's nobody reading those streams, what to do about it. Well, if you want to output that and push it into a database or data warehouse, or multiple databases or data warehouses, you'll create these so-called pumps that will be doing the selecting from and inserting into this external system. And by doing that, selecting from it will draw the data through and cause the system to materialize and compute the things that you want to be computed, because you want to materialize them in the outside database. And then once the values are there, of course, you can then enhance them by joining the stream against the table if you want to, or using other UDX mechanisms that will otherwise process the data against those external systems. Yes, when you come to replaying, you can we can operate upon the embedded timestamp, or we can supply a timestamp. If we are operating upon embedded timestamps and those are stored, then we can replay those streams and put them through any other queries, or you can replay the logic that ran into it. In many cases in the operational world, if you take like the kind of the Splunk type scenario, people are effectively basically storing, one of the views is to store all of the incoming data that you are processing. And then unlike a Splunk, we can create any number of derived views and be able to store those as well. So given the sort of relatively inexpensive approach now using Hadoop to store information, a whole bunch of things become possible that weren't possible before. And then when you come to replay, you can actually replay a subset of the information. You could, for example, I want to replay the stream or accounts the records that applied only to a particular geography or a particular account, and so on. And then you will replay them through the streams and perform the analysis and take the results. And then you can decide whether you want to visualize them, want to persist them, or what you want to do.
Good stuff. Well, we got a bunch of questions here, Damian, so hopefully you can stick around for a couple more minutes. I'll try to get through them.
Stay as long as people want.
Okay, good. So one of the questions from the audience member reads, is your product about making streams first-class citizens in a relational database itself, like TrueViso tried doing?
Well, we aren't there to compete with databases, so we didn't think that made a lot of sense, and we built this SQL engine. TrueViso was based around, it was a complex event processing system, I believe, originally. They were focusing on that, but they built it around Postgres, and they built stuff on top of Postgres, and that's the path they took. We decided that this was such an important area, we wanted to create one of the few all-new relational engines and have it designed specifically for processing these streams at very high performance. and understanding what it would mean then to process unstructured data and to be able to process it in the kind of the modern multi-core hardware. And so that's the path that we took. They are first-class citizens because we're based on standard SQL. They look like streams are ours for us. As I said, infinite tables where records are being appended to. You do have this, they do need to have this monotonically increasing key, which in most cases is a timestamp, and that's because we want to be able to process queries continuously over windows that operate over these keys. But the windows do not have to be just over time. They can be based on numbers of records as well. So you may have a window of 50 records, 1,000 records, 1 million records. It really depends what you want. The timestamps, by the way, can vary from milliseconds or sub-milliseconds through to months. It really is. And you can have, as I said, different windows and different queries, multiple windows within a single query.
That's very interesting.
Helps answer.
Yeah, no, it is. And just out of curiosity, what you guys are doing is very, very interesting, and I would border on saying unique. There are other companies, obviously, they're working with streams. You mentioned Splunk working with log files and so forth, but I have to think that part of the challenge of being able to get the benefit from a tool like this is in just understanding which data sets you pull, how you pull them in, and as you're discussing right now, what the windows are, what the triggers are, so on and so forth. Do you guys typically work with a handful of systems integrators or consulting firms who really understand what you're doing and get it, or do you provide some of that consultancy in pre-sales or after sales has been made?
Well, all of the above, actually. We provide consulting and consultancy both to partners that have, systems integration, business intelligence, SQL skills, etc. We also provide consulting services directly to customers that want us to help them be successful with the product. But we have been very careful to try and, again, not invent new stuff ourselves where we can. There's enough invention underneath the hood. So we have stuck strictly to the SQL standard. All of our documentation is available online, so you can look through it and see exactly how we do everything. And the tools that we use for example, for monitoring and managing the system is a plugin into Eclipse, again, an industry standard. So the idea is that people should be immediately familiar. If they use Eclipse or they use SQL, they understand what the SQL standard is, then they can be productive very quickly.
Okay, good.
Now, there are complexities, by the way, I should say. There are complexities but they are in complexities that are inherent in doing continuous processing. You have to think about the time windows that you want to operate with. So it kind of forces you to think through what do you mean when I'm joining this stream of machine data with this other stream of machine data? What do I do if the data come in 10 minutes late? It forces you to think about that, but it's good because you're going to have to deal with it eventually at some point in time.
Right. Okay, good. And in terms of the actual implementations, this is done on-premise, right? Or do you offer a hosted solution too?
No, we also offer this currently over Amazon EC2.
Okay.
And it's very straightforward for us to offer this on other cloud infrastructure if anybody has a particular desire. We only support Linux for the actual execution servers, the F servers, which are the stream processing SQL engines. But for some of the tool sets, we also support on Microsoft Windows. So that's the current sort of test matrix right now, or the supported matrix.
Okay, here's a very, very specific question. One of the attendees asks, I expect that you support queue-based publish-subscribe. How do you make a set-based language like SQL do cursor-based operations between checkpoints, compute points, and how do you ensure data locality within those cursor operations, i.e. local lookups, etc.?
Well, we're not performing cursor-based operations as such. We provide I believe we provide, you're getting near the edge of my technical knowledge now, I believe we provide cursor-like facilities just to sort of simplify the writing of UDXs in Java as we generate the sort of the code for you. But we aren't transacting anything, and you're processing records, in the order that they come in. We ensure that they are sort of time-ordered, or whatever that monotonic key is that behaves like time. So in that regard, we are, we are the declarative subset of SQL that's focused on that's not focused on transacting or side effecting, or the imperative part. It's not SQL PL. and it's not really the cursor-type stuff that people have used to sort of otherwise position data. You can't jump randomly around where you are. You have to be able to process this as a continuous query.
And I put up this slide because I think it really, and normally it's animated, folks, but WebEx does not support that animation. But can you kind of speak to this as the secret sauce in your parallelization and how that works and why this is what
animated? You'll just see all of these records coming in continuously and flowing across. So pipelining, it's the same sort of idea that you have in car assembly. Even though it takes a hell of a long time to assemble a car, you go through many, many steps in the process. Cars can keep rolling off every 5 seconds. So it's a way of doing parallelism by breaking down a task into sequences of tasks, and each of those sort of worker components is operating upon a piece of the data at that particular time, and all the while more data are flowing in through the pipeline. That's the whole idea behind that. That's the left to right. And as you branch out, where a particular, there are multiple arcs emitting from a single node, that's the sort of superscalar or data partitioning. Because we aren't transacting or side effecting the data, we can readily, if you like, spray the data across multiple processes that can then perform different computations in parallel. And so it becomes fairly clear, hopefully, as you think about it, what pieces, there's an implied ordering of what has to happen first based on time, but this graph tells you, it kind of constrains what it means to do something in a computationally valid way. And it's exactly like hardware, by the way. Today, hardware takes exactly the same approaches with pipelining and superscalar to be able to do things in parallel in real time. And we use timestamps to make sure that the incoming data are valid. In hardware, you have a clock pulse, which is really similar. It makes sure that the data are ready before the gate fires.
Okay, good. And we're past 70 minutes, so I'm just going to throw one last question. But if I missed any in here, folks, we will pass all these questions on to Damian to answer offline. But here's a good one, a last final question, I suppose. One of the attendees asks, how do queries call each other? If it's an automated process, how is the system regulated?
That's an interesting question. So we use the mechanism again. We didn't want to invent something new. So there are schemas that provide, if you like, partition namespaces, and so exactly the same kinds of techniques that you're using in data warehouses to handle the complexity of what query can mention what other query we use within our mechanism too. And then we also extend that again according to the standard. So you can, just like you can have foreign tables within the SQL standard, you can have foreign streams. And those foreign streams then are able to be accessed by other systems that have the rights to be able to access those foreign streams.
Okay, good. And I'm just going to push a couple last slides. I love this material that Mark put together. And folks, we will, of course, archive this webcast. You can hop online to InsideAnalysis.com, look under the webcasts section to see all the recent events. It's quite a litany of events. All the big players in the business just about have been in the briefing room. So with that, folks, we're going to bid you farewell. A very, very big thank you to Damian Black of SQLStream and our friend Mark Madsen from Third Nature. Like I say, we will archive this webcast for later viewing. This April is coming up is Intelligence Month and Integration, then Database. And with that, folks, we're going to bid you farewell. Thank you so much for all these wonderful questions. We'll catch up to you next time, folks. Take care. And speakers, stick around for a quick post-conference. And that's the end, folks. Take care.